This next series of videos include possibly the most mathematically challenging material in the whole module. However, the good news is that once we're over this, it's all downhill from here, at least mathematically. And the topic is second-order step responses. What happens to circuits with two poles in their frequency response when they are given a step at their input? First, a quick reminder of second-order frequency responses. In the general form, you can write the denominator, that's the terms containing the poles, in this format, having factorised the quadratic that we get in the denominator into two terms, one corresponding to the first pole and one corresponding to the second pole. However, we don't usually do that because solving the quadratic equations is a bit tiresome, so we usually characterise them in terms of a resonant frequency, omega naught, and a Q factor, Q. The resonant frequency is the geometric mean of the poles. The Q factor is, for a high-pass filter or a low-pass filter, it's the gain, the amplitude gain at the resonant frequency, and for a band-pass filter, it's the resonant frequency divided by the 3 dB bandwidth. At least this is true when the high-pass filter and the band-pass filter have their zeros at 0 Hz. You can determine the poles from this expression here, which is just solving this quadratic equation in the general form, giving the poles as functions of the resonant frequency and the Q factor. Right, that's the frequency response. However, as we've seen, when the input is a step, we cannot easily use the frequency response because an input step is not a sinusoidal oscillation. So we have to go back to the original differential equations. And for the configuration which we've previously used to illustrate the low-pass filter, we can write the equations using techniques of nodal analysis, looking at the resistor here, applying Ohm's law to the resistor, A, which is the input, which is going to be a value of 1 for all times of interest, because we're not really interested in times before the step arrives. So A is going to be equal to 1 for all of the times that we're interested in. A minus Y, where Y is the voltage at this point in the circuit here, is going to be the current times the resistance. Now it's the same current flowing through all of these components, so we can write the voltage across the inductor, which is going to be Y minus X, where X is our output, is the inductance times the rate of change of the current, because that's what inductors do. The voltage across them is the value of the inductance times the rate of change of current flowing through them. And then we've got the formula for the capacitor, which derives from Q equals CV and tells us that the current is equal to the capacitance times the rate of change of the voltage across the capacitor. And in this case, that's just X, because the voltage across the capacitor is the difference between X and 0. Just X. Right. Eliminating Y from these first two equations gives me, from this equation here, Y is equal to 1 minus IR. Substitute that in here, we get 1 minus IR minus X equals L di dt. I can directly substitute in for I, but to substitute in for di dt, I need to differentiate this expression as well. That would give me di dt equals C d2x dt squared. And I can now substitute in for both I and di dt and get 1 minus RC dx dt minus x equals LC d squared x dt squared, which, just moving the terms around, gives me LC d squared x dt squared plus RC dx dt plus x equals 1. And that's a second-order linear differential equation, which we will have to solve to work out what the step response of this network is. Now, from the mathematics module, you should have learnt already that you can solve this sort of linear differential equation using a characteristic equation, auxiliary equation, and particular integral method. And that would result in solutions of the general form x is a function of time, a constant plus a constant times e to the power of r1t plus another constant times e to the power of r2t, where r1 and r2 are the roots of the auxiliary equation. And you generate the auxiliary equation by taking the coefficients of the derivatives of x and forming a quadratic out of them. So in this case, that would give LC r squared plus RC r plus 1, just looking at the coefficients of x, equals 0. And that would be our characteristic equation in this case. We can solve this equation using the standard quadratic equation formula, and that would result in the values of the roots here r being given by this expression here. Now, if you work out what the frequency response of this circuit is, bearing in mind that our circuit at the moment is just a voltage source here, going into a resistor and an inductor, and the output being taken across a capacitor, then the frequency response of this circuit is 1 over 1 plus RC j omega plus j omega squared times LC. And we would find the poles here by solving the quadratic equation on the bottom. The poles are the values of j omega for which this denominator is equal to 0, so you would find them by solving the quadratic equation there. And you might notice something. This equation, which finds the poles from the frequency response, and this equation, which finds the roots of the characteristic equation in solving the second order differential equation, and gives the coefficients of the term e to the power of something t in the solution to the step response equation, they're exactly the same quadratic equation. Therefore, they will have the same roots. And that gives this very important result. The poles of the frequency response are the roots of the characteristic equation when we're solving for the step response. And therefore, we can in general write our step response in the form A plus B times e to the p0t plus c times e to the p1t, where p0 and p1 are the poles from the frequency response. All we have to do is work out the values of the constants a, b and c from the known starting values of the voltages and the currents in our circuit. Now, you might also remember that when we analysed the low-pass filter, the band-pass filter and the high-pass filter, their poles were in exactly the same place in each case. The only thing that changed was the number of zeros that we had at 0 Hz. And since these coefficients here are related to the poles, they are going to be the same for the low-pass filter, the high-pass filter, and the band-pass filter's step response as well. The only thing that should change for the step response of these 3 different filter types is the values of A, B, and C, these constant coefficients, these constants of integration. And it's how to work out the values of A, B, and C that we'll be looking at in the next video. That's all I wanted to do in this video. Next time, evaluating the constants A, B and C and finalising our derivation of the step response of this low-pass filter.